You ever see one of those giant excavators just effortlessly scoop up tons of rock and dirt and just wonder, how in the world does that happen? How does a machine that massive move with that much power, but also with such incredible precision? Well, today, we're going to dig into the amazing hidden force that makes all of that possible.
Right. Let's get right to the heart of it, because it really seems like it shouldn't work. You know, you've got an operator in a cab, they pull a small lever, a pretty simple movement, and that one action commands this gigantic steel arm to lift something heavier than a car. What is the secret connection between that little tiny movement and that absolutely immense power?
So the first clue to solving this whole mystery isn't some complex system of gears or a city-sized engine. Nope, it's something much, much simpler, a liquid. The entire secret, the whole shebang, lies in harnessing the totally unique, almost magical properties of fluid.
And that brings us to the big word for today, hydraulics. That's really all it is. It's the science of putting a liquid under very specific controlled pressure to do incredible amounts of work. This one single principle, it's the foundation for pretty much all heavy equipment out there.
So, you might be asking, why a liquid? Why not something else? Well, it's got these three amazing advantages. First, it can flow anywhere, right? It'll conform to any pipe or cylinder you put it in. Second, and this is absolutely crucial, it is practically incompressible. You just can't squeeze it down into a smaller space. And third, and this is a really big one, when you push on it, that pressure gets sent out equally in every single direction at once.
To really get this, just think about the difference between a liquid and a gas, like air. If you tried to do this with air and you pushed on it, the air would just compress. It would get squishy. There'd be this spongy delay before anything happened. But a liquid? Oh, a liquid acts like a solid steel rod. The very instant you push on one end, the other end moves. There's no squish, no delay, just pure, immediate transfer of force.
And yeah, this is the whole point right here. Because that liquid can't be compressed, it becomes the absolute perfect vehicle for transmitting force. It's like a solid link between the engine and the bucket, turning a simple fluid into raw, unadulterated power. But how does it actually multiply that power?
So, okay, moving force from point A to point B is one thing, but how do we make it stronger along the way? For that, we've got to go back, way back actually, to the 1600s, to a genius by the name of Blaise Pascal. His discovery is where the real magic of force multiplication happens.
Okay, Pascal's law sounds a little dense, I know. But the idea behind it is actually incredibly simple. It just means that if you have a sealed container full of liquid and you press down anywhere on it, the pressure increases everywhere inside that container all at once. The exact same pressure is pushing on every single surface inside.
Which brings us to this beautifully simple formula. This is the key to everything. The amount of force you get on the other end is just the pressure inside the system multiplied by the surface area you're pushing on. Think about that. A bigger piston means more area, which means you get way more force, even though the pressure inside the liquid is exactly the same.
Let's put some numbers on it. This is where it gets really cool. So imagine you push down with 500 pounds of force on a small piston. That creates, let's say, 40 pounds per square inch, or PSI, of pressure inside the liquid. Now remember Pascal's law? That same 40 PSI is now pushing everywhere, including on a second, much larger piston. And because that piston has more surface area, that same 40 PSI pressure generates a much bigger output force. In this case, over 1,100 pounds. You've just more than doubled your force. That's the magic of mechanical advantage right there.
Okay, but hang on. This leads to one of the biggest misunderstandings in all of hydraulics. We've been talking a lot about pressure, but where does that pressure actually come from? The answer is probably not what you think, and it's one of the most important aha moments you can have.
Get ready for this. The pump, the heart of the hydraulic system. It doesn't actually pump pressure, it pumps flow. It just creates movement of the liquid. Let that sink in for a second because it's a huge deal. So if the pump isn't making the pressure, what is?
Think of it like a river. If the pump is just pushing liquid through a big, wide-open pipe, that liquid is just going to cruise along happily. There's movement, right? That's your flow. But there's nothing for it to push against, so no pressure builds up. A pressure gauge on that pipe would literally read 0.
But the moment that flow runs into some kind of resistance, like if you try to squeeze it through a tiny little opening, or you make it push against a heavy cylinder to lift something, that's when the liquid starts to back up. And that resistance to the pump's constant push, that is what creates pressure. So here's the key takeaway. Pressure is just resistance to flow. That's it.
And engineers are super clever about how they use this idea to design hydraulic circuits. For instance, in what's called a series circuit, the oil is forced to go through multiple roadblocks one after another. The pressure needed to get through all of them just keeps adding up. But in a parallel circuit, the oil gets a choice. It has multiple paths it can take. And just like water flowing downhill or us trying to avoid traffic, it's always going to take the path of least resistance. It'll go down the easiest route that needs the lowest pressure.
All right, so now we have all the clues. Let's put all the pieces of our puzzle together and finally solve the mystery of that incredibly powerful excavator.
It really all boils down to these three key ideas. First, you've got the incompressible liquid, which acts like a solid steel rod, transferring force instantly. Second, you have Pascal's law, which is our force multiplier, letting us turn a small push into a giant shove. And third, the engine's pump is constantly creating flow, and the work itself, that big pile of dirt that needs lifting, provides the resistance that generates all the pressure we need to get the job done.
So, the next time you see a piece of heavy machinery working, you'll know its secret isn't just about brute strength. It's about the elegant, incredibly powerful physics of a trapped fluid. And it kind of makes you wonder, right? What other invisible forces are out there, hiding in plain sight, making our whole modern world possible?